Okay, so the immune system is very important for any for any organism because it will help this organism to survive attacks that normally can be found in the environment. As well, it protects us from diseases like cancer, for instance, and also it helps us to stay healthy when we have contact with allergens, for instance. So here you can see a lymphocyte or a couple of lymphocytes attacking an antigen. So first let's look at some terminology. So immunity is the ability to fight disease. And in the case for us, we will be looking at diseases caused, of course, by microorganisms. Also, microorganisms produces toxins that can be dangerous for us, or they can release waste products, like in the case of parasites, and then they can set an immune reaction. So this immunity helps us then to protect against everything like that. So it can also refer to the response that we have after we have been exposed to environmental factors, agents like pollen, dander, anything that it can cause an immune reaction. And then we have a subdivision of immunity that is called innate and acquired. Innate immunity is the one that we're born with, and it has different structures that protect us. For instance, we are born with skin and mucosas. So that's one of these mechanisms of defense. Also, we're born with certain molecules like the complement system that as well protect us from anything that can harm us. So the strong immune system then consists of physical and chemical barriers or protections that inhibits microbial growth or destroy the microbes. And here we have some of the components of this innate immunity and the components of the adaptive immunity. So for innate immunity, we have the first line of defense like skin, mucous membranes, and the normal microbiota. For the second line of defense, we will have cells of the blood like phagocytes, which will be neutrophils, macrophages, eosinophils, basophils. And then we have dendritic cells that are found within little structures in our body that we call lymph nodes. And as well, we have molecules that are part of the inflammatory reaction. So inflammation is part of the second line of defense. And as part of inflammation, we have as well molecules like tumor necrosis factor, for instance, that can induce fever. And with this, we will have a higher temperature in our body that it can help to reduce the number of microorganisms. And then we have some antimicrobial substances that are produced by the normal microbiota and also by the glands in our body, like the sebum that lubricates our skin. It has acids, so it has fatty acids. The earwax that we have in our ear canal, it is part of these fatty acids that can destroy microorganisms. So we have these antimicrobial substances. And then for the third line of defense, we have cells that are also part of the blood cells and that produces certain proteins, but they are part of the adaptive or third line of defense. So for instance, we have T lymphocytes and B lymphocytes. And then B lymphocytes produces antibodies. So here we have another subdivision of this adaptive immunity. So adaptive immunity can be subdivided into naturally acquired or the artificially acquired. So this adaptive immunity is called adaptive because it responds differently. It adapts to whatever is the molecule that is harming us. So for instance, it is not the same responding for getting in contact with pollen than with the molecules that are on the surface of bacteria. And then our T lymphocytes and our B lymphocytes adapt the response based on how dangerous these attacks are considered. Okay? So now, for naturally acquired, we have active and passive. Active is when you produce your own antibodies. Okay? And then passive is when those antibodies were produced from someone else. So in the case of naturally acquired, we have active immunity when someone has antigens entering into their body, and then the person starts developing antibodies and a specialized type of lymphocytes for this response. And then the naturally acquired is, for instance, when we're born, we all have received a source of antibodies from our mom. And these antibodies are IgG. So IgG, it is an antibody that crosses the placenta. And that source of antibodies lasts us for around 9 months or so. And the reason for this is because during those 9 months after we're born, and we still have antibody or immunity coming from our mom, we have the chance to develop our own immune system. So we train it. And that's why babies crawl, grab objects, put it into their mouth. And then, of course, with the first meal, they will start colonizing their large intestine and their oral cavity. And that helps to set the normal microbiota that is going to protect against pathogens. Okay? So that's part of the natural acquired immunity. So, but now, if the baby was breastfed, now it's going to have another source of antibodies, which is going to be IgA or immunoglobulin A. So this one is an antibody So these antibodies found in several secretions, including breast milk. Let's put here breast milk, saliva, tears, and semen. So then the baby, you will have a secondary source of antibodies if he was breastfed. And now we have artificially acquired immunity that also can be subdivided into active and passive. So we have active when we have introduction of antigens that are found in vaccines, and that help us to produce antibodies and specialized lymphocytes. So in this case, it can be through vaccination or also through natural infection. Now, we have, that will be for naturally acquired, for when you got sick. But if you have vaccines given to you, you have either a part of these microorganisms or the microorganism will be killed. And in this case, you will start developing your own antibodies without having to get the infection. So in both naturally acquired or artificially acquired, when they are active, that means that you produce your own antibodies. But naturally is when you get the infection, and artificially is when you get a shot with vaccines. And now, in passive, artificially acquired, it is when you have injection of antibodies produced by either an animal and they were purified and given to you, or maybe it was a clone of a lymphocyte. So there are ways where you can make the lymphocytes to start making antibodies, and then they purify them as well, and then you can get injection of this. An example, for instance, will be these antibodies that are given when someone gets exposed to either a venom from a snake or a black widow, or it could be as well when you get a shot of for tetanus. Okay. So here's a list of all of these components of the first line of defense. So our skin, we have specifically the epidermis, which is made by several layers of simple squamous epithelium, 20 to 30 layers, and it forms a physical barrier. When we shed our skin, more or less like every 7 days, the superficial layers, we are also getting rid of microbes. But also as well, remember, we have these glands, the sebaceous glands in our skin, that helps to eliminate these microbes by maintaining the acid mantle. Okay? And then the mucous membranes. Well, it is an epithelium that it's a little bit more thinner than the skin, because in the case of most of the mucosa in our oral cavity or other areas, we have only one single layer of cells, and this will be columnar cells or cuboidal cells. And since you have less number of cells, less layers, the microbes can penetrate much easier through these mucosas, including the respiratory mucosas. Okay? Now, when we have a wound either in the skin or in these mucosas, it's much easier for the microorganisms to enter. And then we have, so these are the physical factors, and I'm combining them here with some of these chemical factors. So I already told you about sebum, this oil secretion. So this is helping with acidity to destroy these microorganisms. And then mucus itself, it's a physical barrier, it's sticky, so the microorganisms can get trapped really easily. And then we have the lacrimal apparatus that has the production of tears, and then we have lysozyme. You have heard about this enzyme before. So lysozyme, it's an enzyme that so this enzyme breaks down the peptidoglycan layer in the cell wall of bacteria. And then we have not only lysozyme in the tears, but also remember we have IgA, and also we do have lysozyme in our oral cavity secretions, like saliva. In saliva, we have lysozyme, and also we have this IgA. So it is protection for us. And then saliva dilutes and washes microbes from the mouth. And then we have hairs in, for instance, in the entrance for our ear canal, and also in our entrance for our nose. And with those hairs, we prevent the entry of microorganisms into the airways. And then we have as well, of course, our eyebrows, the eyelashes, that helps us as well to prevent entry of microorganisms into our eyes. And then in certain epithelium, like in the trachea, we have pseudostratified columnar epithelium with cilia. And this cilia moves like this, strips away the mucus. If the mucus has microbes, of course, get rid of the microbes. And then this movement is called the mucoescalator or ciliary escalator reflex. If someone smokes, that cilia stays paralyzed, and then it won't sweep away the mucus, it won't sweep away the bacteria, and then the person will have more likelihood to have infections. And then in the larynx, we have this epiglottis. This epiglottis closes the larynx, the voice box, so that when you're ingesting food, the food do not go into the airways for sure, and you won't choke. But maybe some of these microorganisms that will be in food will also not go into the airways. Okay? So that's part of the role of the epiglottis. And then we already saw about the earwax in the ear canal that prevents microbes from entering by destroying them with the acidity. And then we have urine. Urine is a acidic component of our body, it's a waste. And when we urinate, we have a physical factor that flushes away the microbes. And with this acidity, we prevent the growth of microorganisms in the urinary tract. And then we have vaginal secretions. In the vagina, during reproductive stage, we have high acidity levels due to the presence of lactobacilli, and that will help to control these microorganisms from entering into our body. And then for peristalsis, which is the contraction relaxation of the muscles within the gastrointestinal tract. This one will bring as well microbes from proximal areas of the digestive tract into distal areas. And then if the person has an infection, vomiting and diarrhea can help to get rid of these microorganisms. And then in the stomach, we have gastric juice, which is made by hydrochloric acid and some enzymes. So this hydrochloric acid makes the pH of the stomach to be between 2 to 3, and most microorganisms, they don't like that acidity, so they will die in these acidic conditions. Okay, any questions?
Will that person still get the visual active? Just so it's a second those that you know, like it's bad.
Can you repeat higher the question?
So I was thinking, like, because you were talking some of the stomach's very acidic, pH activity, and then like that maybe if it's go to the stomach and say can't handle the conditions of that, and releases endotoxins, and I was wondering if it would still cause
So the effect of toxins in our body, it will activate the immune system as well. Uh, when you have some of these toxins, they bind to receptors that we have in the cells. And then the cells, secondarily, will release chemicals that will attract the cells of the immune system. And then part of this will be the release of cytokines that will open up the blood vessels. And when you have the opening of the blood vessels, you will have vasodilation, and then you will have this endothelial cells separated, and then you will have this plasma exiting the bloodstream, the circulatory system that causes septic shock. But when that happens, typically the person has a very low response of the immune system. And some of these endotoxins, for instance, can go into the hypothalamus and can activate fever. And that fever, it helps to control the microbial growth so that you don't have as much toxemia, for instance, if the microorganisms are growing and they are releasing toxins into the bloodstream. Does that?
Yeah.
Okay. Yeah, we can talk about more details later, but hopefully I at least I answer a little bit of your question. Okay, now for the second line of defense. So we have phagocytes and natural killer cells as defensive cells. So in our bloodstream, we have white blood cells and red blood cells. So the white blood cells themselves are subdivided into two kinds. We have agranulocytes and granulocytes. And then some of them, they are part of the innate immunity, and some of them are part of the adaptive immunity. So we have leukocytes. And for leukocytes, we don't have huge numbers as the number of red blood cells that we have, but these are the types of leukocytes that we have. So these are what we call granulocytes. And then we have monocytes and lymphocytes. Now, these four in here are phagocytic. And now, lymphocytes are subdivided into three types. So we have B lymphocytes, we have T lymphocytes, and we have NK cells. So NK stands for natural killer cells. So these natural killer cells are 5%, so they are the minority, and these ones are more abundant. Now, all the granulocytes plus the NK cells are part of this second line of defense. And now these two, the B lymphocytes and the T lymphocytes, are subdivided into more classes. So for lymphocytes B, they can be naive or they can be plasma cells. And the plasma cells secrete antibodies. Now for T lymphocytes, we have helper, which are also known as CD4 plus, then we have cytotoxic T cells, which are CD8 plus, and then we have regulatory, or suppressor. So those are the classes of white blood cells and why do they play a role. Now, this type of lymphocytes, B and T, are part of the acquired immunity or adaptive. So these ones are very important after we're born to train them properly so that we can respond to the different antigens that we get in contact with. The other ones, they will respond all the time, basophils, eosinophils, neutrophils, monocytes, and NK cells in the same way. That's why this system, innate, is also known as non-adaptive. And both of them work together to help to have a strong immune system so that we can get rid of microorganisms, and then we can also fight cancer cells, and then we can be healthy by fighting also molecules that can trigger the immune system like pollen, dander, etc. So those were the defensive cells. Now for inflammation, we have different type of molecules that can cause inflammation. It will be some inflammatory chemicals like histamine, for instance. Also, it can be tumor necrosis factors, some interleukins that are chemicals that are released by several cells, including these lymphocytes. And then antimicrobial substances, we have the complement system, which is a series of 30 subunits of proteins, 30 or so, that are produced by the liver, and that they will start forming complexes so that you can form pores in bacterial cells. And this complement system is inactive until it is activated by the presence of microorganisms. And then we have interferons. The interferons are produced by virally infected cells. And these interferons will be diffusing to the sites when you have an epithelium, for instance, and then the neighboring cells, they will endoscytose these interferons, and they will start shutting down these receptors for viral for viruses, so that they will be immunized. And these interferons, they are so effective that they have been artificially made as well, and these are part of the drugs that are used to treat viral infections, like for instance hepatitis C. They cost a lot. Anything, guys, that has to deal with viruses, like antiviral drugs, they cost a lot to make them. Okay, but they are important to have them in certain viral infections. And then we have as well iron binding proteins. So remember, there are some, we saw in the previous chapter, there are some molecules that still are iron that is produced by certain microorganisms like siderophores. So with this siderophore, they store our iron, and then with these iron binding proteins, we steal it back. So it's a fight between the microorganisms and us. Now, oftentimes then, someone who has an infection will have anemia, because if the microorganism uses iron, then it will be stealing this iron. And then, of course, remember that iron is necessary to make red blood cells. And then we have antimicrobial peptides, or AMPs, that inhibits the cell wall synthesis, and is produced by certain microorganisms that we have. So these are some molecules that will be competitive for these. So here we have an example then of one of these phagocytes, how they ingest microorganisms by binding first these microorganisms with some receptors that we have in these cells. So this is a macrophage, so this is an scanning-like micrograph. And then we have, for instance, in this macrophage, a molecule that is called toll-like receptor, or TLR. This TLR is going to bind into the cell wall of this microorganism a molecule that this microorganism that is called PAMP. So it's a specific molecule that is found in the peptidoglycan. And then when you have this physical contact, then you will trigger endocytosis by this phagocyte, and then you will form a vacuole. So this vacuole is going to be called phagosome. And then these phagocytes have lysozymes that they have produced in the Golgi apparatus. So then they will fuse these two vacuoles, the one with lysozymes, with the one with the bacteria. So you will form what is called a phagolysosome. And it can be an early phagolysosome or late phagolysosome. As time progresses, these enzymes starts breaking down these bacteria. And then you will have indigestible material that is going to be now extruded from this phagocyte through exocytosis. And then sometimes what it will happen is that these molecules that are found in here will be important to present into these lymphocytes so that you can start an immune reaction. So you will have a cell that is going to be called antigen-presenting cell, so that you can attract the phagocytes and that you can start activating many cells so that you can get rid of all the microorganisms that will be found in your body. So here we have an example of an scanning electron micrograph showing you how this macrophage is going to start endocytosing this. But first they make this physical connection between the toll-like receptor and this molecular pattern molecules or proteins that these microorganisms have. So what are the specific roles of the different type of white blood cells that we have in our blood? Well, in the case of white blood cells, so we have between 5,000 to 10,000 per microliter of blood. This is compared to around 5 million per microliter that we have of red blood cells. When someone doesn't have an infection, which is most of the time, we don't require to have huge number of leukocytes. But what do we require all the time? Well, to bring oxygen to our cells, right? So that's why we have millions of red blood cells in comparison to very few leukocytes. But then when you have a high number of leukocytes, you call that leukocytosis. Like, let's say that you have about 14,000 leukocytes per microliter of blood. So you call that leukocytosis. And then, depending on which leukocyte it is increasing number, it is what you will think is going wrong. So we have neutrophils, which are also known as PMNs, polymorphonuclears. And they are called polymorphonuclears because if you see there, so this is a leukocyte here, a neutrophil in this left upper part. So those kind of dark reddish or dark structures that you see inside the cytoplasm, those will be the nucleus. And the nucleus, or that will be the nucleus, sorry. So that nucleus is segmented and it takes different shapes. So in there, I mean, it's hard to predict shape, but that's why it's called PMNs, polymorphonuclear. So it looks like if you had more than one nucleus, but it's actually one, and it is continuous in these little spaces. Okay, so now for these leukocytes, they have the function to phagocyte. So the granulocytes, basophils, eosinophils, and neutrophils, plus the monocytes, they are macrophages. So they phagocytose or they eat. And specifically, basophils, eosinophils, and neutrophils, they are called microphages because they're not as large as the monocytes to eat a lot, but they still eat a little bit. Okay, and these ones, they form between 60 to 70% of the leukocytes. That's the percentage. So neutrophils. It's 60 to 70% of the leukocytes. The second most common one, let me change, is going to be the lymphocytes. So lymphocytes makes between 20 to 25%. We're putting it here. And then the lymphocytes will be in charge of destroying cells through cytolysis or apoptosis. So here we have a T cell, and here we have a B cell. And it is hard to know without these molecular markers like CD8 or CD4 plus if you have a B or T lymphocyte. I don't know how they did in there. Possibly they just studied the molecular markers and then they have it separated. And this is a T cell, this is a B cell. But it's hard to know. Now, one characteristic of lymphocytes is that they have a large nucleus, which is this, and very little cytoplasm. Now, in the case of the B cells, the ones that produces antibodies, these ones, they will have a smaller lymphocyte and a larger rough endoplasmic reticulum when they're producing antibodies. That's a shift that you will see. And when that happens, you will have what is called a plasma cell. And now, the next abundant white blood cell will be eosinophils. Or sorry, monocytes. Sorry, let's go back. So it will be monocytes. So monocytes makes between 3 to 8% of leukocytes. So they are the precursor of macrophages. This is the largest white blood cell that there is, and it has like kind of a horseshoe-shaped nucleus, as you can see here. And when it is found in blood, it is called monocyte. But when it exits the circulatory system, it's going to enlarge more, and it's going to be a macrophage. And then some macrophages will have a different name based on the area of the body where they are found. Like if they're found in the brain, they will be called microglia. If they're found in the liver cell, they're going to be called Kupffer cells. If they're found in the skin, it will be dendritic cells. If it's found in the lungs, they will be called dust cells. Now then, the next one, the next abundant type of leukocyte is going to be eosinophils. Eosinophils makes between 2 to 4% of the leukocytes. These ones are characterized by having a lot of granules in their cytoplasm, as you can see here. And it has kind of a almost segmented nucleus. And these granules will be released when someone has an allergy or when someone gets in contact with a parasite. And these granules are going to be red in color. It takes this eosine, which is a red dye, from when you're staining these cells. So, functions to produce toxic proteins against certain parasites. And some of them can be phagocytic cells. So those are the eosinophils. And then the less abundant type of white blood cell are the basophils. So these basophils makes between 0.5 to 1%. Typically it's like less than 1%. So these basophils, they have so much abundant granules that you can hardly see the nucleus. and the granules are purple in color. And in their granules, they have histamine. So when someone has an allergic reaction, these ones as well can increase in number. So then there is, of course, when you receive a study for a differential, this is a differential like knowing how many percentage of each of these you have as a leukocyte. You ask for that when you're trying to see what is wrong with the person's body. And then you start seeing whether you have increased number of lymphocytes, monocytes, eosinophils, etc. So then in this differential, they will give you the specific percentages according to the lab and the numbers. They not only give you the percentage, but also they give you the numbers. And that will be your reference point. Now, anything that it's above typically is OSIS. You call it OSIS, like leukocytosis, lymphocytosis. Okay? And anything that is dropping, you call it anemia. Okay? So you can have, for instance, lymphopenia. And there is an acronym because unless you're looking at those numbers all the time and then you have a super good memory, of course you will know the numbers and the percentage. But let's say that you don't remember and someone may ask you, okay, what is the third most abundant type of leukocyte? So then you will remember a phrase: never let monkeys eat bananas. Okay? So then you start thinking, okay, monkeys is the third word. So then it will be monocytes. Okay, so that's kind of a jingle there. And then if they ask you, oh, which one is the less abundant? Well, bananas is the less, so basophilus is less than 1%. Neutrophils will be the cells that increase when you have a bacterial infection. Eosinophils increase when you have parasitic infection or when you have an allergy. And then lymphocytes and monocytes, they increase in number typically when you have a viral infection, but also when you have a chronic infection of any kind, no matter which type of infection. Okay? And then we have these dendritic cells that are derivatives from monocytes, and they are phagocytic, and they are found in lymph nodes and also in our skin. And they are antigen-presenting cells. So it helps for bringing antigens into cells that respond to these antigens, like lymphocytes, and then you start a strong immune response. So now let's look at greater details for the T and the B lymphocytes, which are part of the adaptive immunity. So these two work together to start forming clones of cells that are going to form antibodies or cells that are going to attack other cells. So that clonal expansion will lead to differentiation of these T cells and B cells of different kinds. So it does not only make a huge number of cells, but what cell is going to do what. So we have then, in adaptive immunity, we have a type of immunity that's called humoral and a type of immunity that is called cellular. What does humoral and cellular immunity means? Well, cellular immunity, it is produced by the T cells so that they can destroy cells that are intracellularly infected. Viruses infect cells internally because they are intracellular parasites, so they cannot live outside of the cells. So they will be destroyed by T cells, T lymphocytes. And then we have some bacteria that are intracellular, like chlamydia, rickettsia. So these will be infected, these cells in the body will be infected no matter where they are. And then these T lymphocytes will come and destroy these cells. And now humoral immunity, it is given by the B lymphocytes, specifically the plasma cells, because you will have soluble microorganisms in your body. Like it can be found, some microorganisms in urine, it can be found in the blood, in the cerebrospinal fluid. And in this case, the B lymphocyte will produce antibodies, and these antibodies will block these microorganisms from attaching into the cells. And it is called humoral because ancient Greek doctors believed in the presence of humors in our body, including our fluids, and then that will include all these humors, and then they call it that way, the fluids in our body, they will call humors, and then that's how we end up with this name still talking to today. Okay? So then these cells secrete antibodies to bind soluble antigens and freely circulating pathogens, forming humoral immunity. Okay, any questions so far? Okay, now let's look into what is hypersensitivity, what are the kinds, and we're going to see what are the mechanisms of each of these hypersensitivity reactions and how serious they are, and how we test for some of these hypersensitivity reactions, and we're going to see what is desensitization and blocking antibodies. So hypersensitivity reactions are reactions of our body, of the immune system, that are exaggerated. So our immune system, it's supposed to find antigens or something that is going wrong, like a presence of microorganism, respond to it, destroy it, and that will be it. Okay? Do not overreact. But in the case of hypersensitivity reaction, you have an exaggerated immune response that can damage our body. And hypersensitivity basically is the fancy name for allergies. Okay? And then allergies are subclassified into 4 different kinds. Now, before we go into the explanation of these, let me give you some definitions. So, for foreign antigens and self-antigens. Well, an antigen is a molecule or a substance that can be recognized by the immune system and trigger an immune response. Not all the antigens can trigger an immune response. So we can have contact with many antigens in our environment. And we might not classify them or recognize them as foreign, and then we don't trigger an immune reaction. But if that antigen enters into our body, and then we trigger an immune reaction, that will be considered a foreign antigen. Now, a self-antigen, or an antigen that is found naturally in our body, can change molecularly and can trigger an immune reaction. If that is the case, that will be now considered a foreign antigen. And then self-antigens, when they are not triggering an immune reaction, which hopefully is most of the time, then they are not considered foreign. They are just self-antigens, okay? So then an allergy or a hypersensitivity reaction can be defined as an immune system response to antigens, leading to damage rather than to immunity. And then some of these allergies are innocuous or they don't cause so much harm, but some of them, they can cause even death. So we have this subclassification of allergic reactions. So we have anaphylactic or type 1, cytotoxic or type 2. We have immune complex mediated or type 3. And then we have delayed cell mediated reaction. So if you want to remember those, remember the first letter of each. Acid, anaphylactic, cytotoxic, immune complex mediated, and delayed. Here is the time that it takes for each of them to develop. So type 1 or anaphylactic can develop in less than 30 minutes. Type 2, between 5 to 12 hours. Type 3, between 3 to 8 hours. And type 4, greater than 24 hours. That's why it's called delayed. Now, for anaphylactic, this is the most dangerous, but it's the most common one, depending on the subclassification. We have a subclassification for these anaphylactic reactions into localized, that can lead you to hives, hay fever, or asthma, but it can be subdivided as well into systemic. And systemic is the one that leads to release of massive amounts of cytokines that can trigger this massive response of our body, leading to a drop in the blood pressure suddenly, and then the person can die. Okay, so these will be the persons who carry their EpiPen. So, how this happens? Well, it's when you have IgE, which is a type of antibodies, binding into a mast cell or a basophil And then these IgE molecules will be cross-bridged by antigens. And then when they are cross-bridged by antigens, they release these massive amounts of chemical mediators of inflammation that can lead to vasodilation and then release of plasma outside of the circulatory system, and then they can lead to shock. But fortunately, most of these reactions are localized. They are not anaphylactic. But something for sure in anaphylactic reactions is that the person has to keep all the things that trigger this immune reaction out of the vicinity, like peanuts, shrimp, etc., because a person can get one of these reactions. Now, here are some examples of these chemical mediators of inflammation. We have histamine, leukotrienes, and prostaglandins. So these will be the ones that are released either by mast cells or basophils when you have these allergic reactions. And this is an illustration of how this happens. So here you have a basophil or a mast cell. All of these is the chemical mediators of inflammation. And here you have some IgE in the surface. So this is how these antibodies look like. And then they bind these antigens to neighboring cells. And then you have massive release of these chemical mediators of inflammation. Okay, so this is all for today. Do you have any questions?